Understand it correctly, we're here on a Monday at 12 noon and we're in G54, 2 lecture theatres along on a Tuesday at 12 noon. Is that what you've been told?
Yeah.
Good. That's good. If we all end up in the same place, that's excellent. And I'm going to be here for 4 weeks and I'm going to be focusing on introducing some aspects of polymer chemistry and talking about the physical properties of polymers. And in the course of those 4 weeks, I'll give you a worksheet to have a go at. And the idea is you have a go at it, because it'll only make sense if you've tried it. Then on the 25th of February, so that's the Monday of week 5 of this semester, we'll be in here and we will go over and give you over that material, and I'll give you some hints as to what you might want to know about for exams and things like that. So that workshop is a good opportunity to get to grips with the material we cover in the first 4 weeks. And you'll see there are a couple of other workshops as well, which will be led by the other lecturers. On the Tuesday of that week, the 26th, Professor Mike Turner will take over, and he's going to be talking about some aspects of polymer synthesis, in particular step polymerization. And he will look after you right up until the Easter break, and there'll be a workshop on the 19th of March. And then after Easter, Professor Yates, who's actually responsible for this course, will take over, talking about other aspects of polymer synthesis. And there will be a final workshop on the 7th of April. The 6th of April is a bank holiday, so you won't be here then. Okay, so that's what you have in store for you. We're talking about polymers. I'm going to introduce polymers for those of you who it's new to in this lecture. I'm going to be focusing on physical aspects of polymer chemistry in the first 4 weeks, and then it'll be about making polymers, synthesis of polymers after that with Professor Turner and Professor Yates. And as we go, you will get bits of work to have a go at to give you practice, to encourage you and help you to get to grips with the material. If you want to know more about polymers, there are quite a few books specifically about polymers. This is a good one because this edition has only just recently come out, and this is written by 2 of our colleagues in Manchester. In fact, from down the road in the School of Materials, Professor Young and Professor Lovell. So this is their book. It covers all sorts of aspects to do with polymers. Introduction to Polymers, 3rd edition. There are copies of that and earlier editions in the main library, and also copies of other books on polymers. There are a number of textbooks. Each have their strengths and their weaknesses, but that's the most up-to-date one available. If you want some very basic introductory ideas and you like surfing the net, you might like to be aware of a website called the Macro Galleria, which is set up by an American university. Being American, it has a particular approach to things. The idea is that the website is like a shopping mall, and you go to different bits of it to get different bits of information about polymers. That's the Macro Galleria. Like anything on the web, not all of it is reliable. But it's got some good stuff, and it's got some stuff which is perhaps oversimplified. So always, when you go onto the web, remember, there is no real check on what's on there. Even books have mistakes. Every book has mistakes. Web material has even more mistakes. So be careful, always cross-check information. Don't assume that everything you read is necessarily right. But if you want some nice, simple ways of getting to grips with some of the basic ideas about polymers, that Macro Galleria website, well, some people like it, some people don't like the approach, but you might want to take a look at it. So what we're going to be doing in the first 4 weeks, where we're thinking primarily about physical aspects of polymer chemistry. And today, this is lecture 1, and we're going to begin very nice and simply with an introduction to polymers. 1 or 2 of you may have already met some of this material, others of you it'll be new. We're going to talk about the different types of polymer we might encounter. I'm going to say just to introduce very briefly a little bit about synthetic polymers, by way of introduction to what Professor Turner and Professor Yates will be talking about later on the course. And I'm going to say a bit about polymer nomenclature, how we go about giving names to polymers. So that's today. Then tomorrow we'll pick up thinking about some natural polymers, thinking about the physical states in which we might encounter them, talking in particular about polymer glasses and about elastomeric polymers. And we'll talk also about the question of why is it that a rubbery material behaves the way that it does. So then next Monday we will start to talk about semi-crystalline polymers. In that context we'll talk about some aspects of polymer stereochemistry. We'll see how some of the ideas that you have met in undergraduate organic stereochemistry can be applied, but perhaps a little bit differently in a polymer context. And we'll talk also a little bit about polymer single crystals. And we'll continue next Tuesday talking about semi-crystalline polymers. If you think about a very basic polymer like polyethylene, it can have a very complex morphology, a very complex way in which molecules are organized. We'll talk about that and some of the experimental techniques that are used to get information about that. And we'll focus on a technique called differential scanning colorimetry, which can tell us certain things about polymers when they go from glassy to rubbery states, when the crystals form and when they melt, that sort of thing. And also say a little bit about polymers which behave a little differently to the rest, because they don't have the same sort of flexibility in their backbones that most polymers do. And that will touch on research that we're doing here in Manchester. The following week, we will start to tackle one of the key questions about a polymer. As we'll see in a moment, the main thing about a polymer is that it contains big molecules. And so the most important question we might ask about a polymer is just how big are those molecules? But the other thing about polymers is that they're mixtures. Again, I'll say a bit more about that. And so we have to understand not only how to work out how big the molecules are, but what sort of mixture we have, what sort of distribution. So we're going to talk about molar mass distributions, and because we have a mixture, we also have to think about averages. So we're going to talk about things like average molar masses, and we're going to talk about some of the experimental techniques that can be used to get information about the size of the polymer molecules, in particular a technique called gel permeation or size exclusion chromatography. We'll also learn a little bit about dilute solution viscometry and how that can help us interpret data from gel permeation chromatography. And that will occupy 2 lectures a week for 4 weeks. And by the end of that, you will have been given a worksheet which will be largely focused on that second part of the course with some problems to try, things to do, make sure you understand the material, which we will then go over in the workshop on the Monday of the 5th week. So, is that clear? Do we know what we're expecting? So this is what we're talking about, polymers. And actually there are an awful lot of things which are polymeric. Some of them are very basic things that make up the clothes we wear. These days, particularly in a university like this, we're interested in researching very sophisticated polymers. Polymers that might be used, for example, as components of electronic devices. Light-emitting polymers. There's a picture here of a device which has a light-emitting polymer display, for example. So polymers include a vast array of things. But what they all have in common is that they contain big molecules, what we call macromolecules, very big molecules composed of repeating units. So lots and lots of different things may be called polymers. We'll try and think in a moment of some examples. What they all have in common is that they contain large molecules, macromolecules. Now, have you all met the idea that polymers are big molecules? So is that news to anyone? Yeah? We all know that. But of course, people didn't always know that. Now, the word polymer was around back in the 1800s. Okay? People had made certain polymers, like polystyrene, long time ago, but they didn't know what they were. They didn't realize they really were big molecules. In fact, they generally assumed that there was some kind of physical association of small molecules. So although there were a few people who hinted at the idea that perhaps these things that we call molecules, called polymers, really could have these enormous molecules, most people thought that was nonsense. And there was this guy, Hermann Staudinger, a German chemist. He was an organic chemist, but he got stuck on the idea that actually these things that we call polymers, and that these include natural polymers, we'll talk about them like rubbers, as well as synthetic polymers, these things that we call polymers really did contain enormous molecules. And in the 1920s, he did a lot of research to try to prove that, and he met a lot of opposition. In fact, he went to a big meeting, we've had a number of meetings, but there was one famous meeting where some very famous chemists objected to Staudinger's ideas. He was told, leave the concept of large molecules well alone. Organic molecules with a molecular weight above 5,000 do not exist. That's what organic chemists believed in the 1920s. And Staudinger had a real job trying to persuade things that actually you could have big, big molecules. But what he said at the time, he quoted someone, you may have heard of Martin Luther, a theologian. He said, "Hier stehe ich, ich kann nicht anders." That's not very good. Have we got any Germans here?
Yeah.
Yeah? You want to give us a good German accent?
Hier stehe ich, ich kann nicht anders.
Very good. Which means here I stand, I can do no other. And actually this is quite an insight into how science works. Because Staudinger at that point was convinced he had enough evidence that polymers were really big molecules, that nobody would believe him, or the vast majority, certainly of his academic colleagues, wouldn't believe him. And the reason was they got stuck with certain ideas that they couldn't get out of. For example, they had stuck with the notion that when you did X-ray crystallography, they knew about X-ray crystallography, a unit cell had to contain more than one molecule, but a molecule couldn't be bigger than a unit cell. And they knew very well that crystalline polymers had small unit cells. Therefore, they said, they cannot have big molecules. Actually, of course, that's nonsense. It's perfectly possible when you have repeating units for the unit cell to be much smaller than a polymer molecule, because a polymer chain, many chains pass through the unit cell, but because we have repeating units, the unit cell is smaller. But at the time, they were fixated on the idea that you just couldn't have molecules bigger than a crystalline unit cell. And because they couldn't get past that, they said, therefore, these molecules can't really be big. So Hermann Staudinger had a real job persuading people, yes, they were. But by about 1929, 1930, people, initially industrial chemists actually, the industrial chemists tend to pick up these ideas, they realised the potential before most of the academic chemists did of what Staudinger was doing. But now, of course, we're all quite used to the idea. It took Staudinger hard work. He had to be pretty determined. He had a lot of students producing a lot of theses before he had enough evidence to convince people. But now we know. We can be absolutely sure these things that we call polymers, they really do contain enormous molecules. And I've said these include things that are natural, they include things that are man-made, synthetic polymers. So, okay, let's have some ideas from you lot. What polymers do we know about? Let's have some examples.
Rubber.
Rubber, right. Okay, what is rubber chemically?
I don't know.
Or at least natural rubber. There are a load of rubbers, synthetic and natural. We'll come to it again later, but natural rubber is what? It's cis polyisoprene. We'll see what that is about later.
That was going to be my second guess.
Well done. Okay, what other polymers do we know about? Well, let's have some ideas.
Cyanoacrylate.
Cyanoacrylate. That's the constituent of superglue. Right, yeah, which cures. Well, it forms a polymer very readily when there's a little bit of moisture present, which is. Okay, what else do we know about?
Don't we use polysiloxane?
Polymethacrylate. What sort of?
Perspex.
Perspex. Okay, Perspex. What methacrylate is it? methyl methacrylate. That's a glassy polymer, and in the UK, we commonly account it under the trade name Perspex. If you go to America, it's plexiglass. It's an organic glass. We're going to talk more about organic glasses and rubbers. What other polymers do we know about?
Polysaccharides.
Poly?
Polysaccharides.
Say again, poly?
Polysaccharides.
Polysaccharides?
Yeah.
Polysaccharides?
Yeah.
Yeah, so sugar polymers.
Yeah.
Okay, give us some examples of a sugar-based polymer.
Can have starch.
Starch? Yeah, that's a good example. Starch is a polymer of glucose. There's another polymer of glucose which is very important, but has very different structural properties to starch. Cellulose. That's a good one.
I said green nylon. It's actually first used in Manchester by Henry Lloyd in clothing manufacturing.
Nylon.
Yeah, 1966.
What type of polymer is a nylon? Chemically, what sort of polymer is a nylon?
It's an addition.
It is an addition polymer? Actually, no, it's not. It's not an addition. It's a condensation polymer. Almost usually. We'll see later. They're polyamides. The nylons are polyamides. Okay. And we'll see an example of the nylon a bit later. Any other polymers we have? DNA, deoxyribonucleic acid, a really important natural polymer. Quite a complex one. We'll come back to the structure of that at the beginning of tomorrow's lecture. Bakelite, a phenol formaldehyde resin. That's an old one. Here's a slightly more modern version of the same sort of thing. These are network polymers. They're thermosets. And they're the sort of thing that's used very often, for example, for electrical sort of switches and such like. But in the old days, of course, Bakelite was first used in all the old radios, the old brown radios, they were all Bakelite. Okay. Actually, if we look around us, what can we see in this lecture theatre that isn't or doesn't involve a polymer?
Light.
Probably the aluminium things, what they say. The aluminium, yeah, the metals. Although quite likely it will have a polymeric coating on it to help protect it. Okay. But actually, look around it. Can you see anything else that doesn't involve a polymer?
Ink.
Now the clothes we wear, they're polymers.
Ink.
Ink? It depends on the ink actually, but yes, the ink. Some inks will actually have some polymers in there as binders, but by and large, the simplest ink would just be a pigment or a dye. If we think about things like paint, then what is it that holds a paint together? It's a polymer. If we think, we've got the textiles here. With wood, we've already said, the main structural constituent of wood is a polysaccharide, is cellulose, and here we've got a covering of something which again is polymeric. We've got polymers on our floor. Pretty much everything we look at involves a polymer. So polymer chemistry is pretty useful. There are very few things that we use, that we make, that don't involve polymers somewhere down the road. And as chemists, many of you, if you go into industry, will be working with polymers. Let's think a little bit more about the different types of polymer we might encounter. How can we break, we've got lots and lots of different things. What they have in common is they contain enormous molecules, but we can break them down, classify them in different ways. So we can think about where they come from. We've already said some are natural, some are synthetic, man-made. And so natural polymers, we mentioned some. There's things like natural rubber, this is polyisoprene, there's the polysaccharides, the nucleic acids, DNA, the proteins, of course, which are polymers of amino acids. And then there are synthetic polymers. And so synthetic polymers are made by taking a small molecule, a monomer, and polymerizing it in some way. And there are lots of different kinds of polymerization. You will learn about a few of them from Professor Turner and Professor Yates. But most of them can be classified into two broad groups: chain polymerizations, which are chain reactions, and step polymerizations, where you have different functional groups and a whole series of separate reactions. We'll say a little bit more about that. But then even if you take, say, chain polymerization, we can initiate the polymerizations in different ways. So you can distinguish, depending on whether we have a radical initiator or an ionic initiator, where we're using some kind of coordination compact contextual initiation, or so on. So ways of breaking all of these different polymers down, classifying them according to where they come from. Are they natural? Are they made man-made? What other differences might we encounter between different polymers? We can think about different structures. The simplest polymer we can imagine is what we'll call a linear polymer, where we just have a long chain of repeat units. So some of the polymers we'll be thinking about will be like that, linear polymers. But of course, we can imagine polymers, for example, where the ends are joined up, so we now have a cyclic polymer. They might be more common than you realise. One of my PhD students discovered this to her cost when he spent several months trying to, making a small polymer, an oligomer, and trying to react the end groups unsuccessfully before she realised that what she had actually managed to make was a load of cyclics which had no end groups. Research can be a little frustrating like that sometimes. Polymers sometimes might have a single linear chain, but quite often, depending on what's going on in the polymerization, you will have little branches. So polymers may have branches, either long dangly branches or little short branches hanging off the sides of the chain. We can have branch polymers. We can these days, if we want to be very patient with a lot of organic synthesis, make very well-defined structures with a very regular branching, what we call dendrimers or dendritic polymers. And then if we think about things like Bakelite, like the phenol formaldehyde resins, when they're polymerized, we end up with a three-dimensional interconnected structure, all covalent bonds. So that's then a network. And network polymers can also be very important. That means that if you look at a network polymer, something like that, I think that's not a good example. That one. Every atom in there, if you ignore the fillers and the extra bits that have been thrown in for the junk, every atom is covalently connected ultimately to every other atom in a network structure. So that is one giant molecule. That's how big a molecule can be. Okay, now we can also, with research, we can start playing games. We say that a polymer is made up of repeat units, but we can have more than one type of repeat unit. We can put more than one monomer in. The simplest polymer just has one repeat unit, or one monomer going into the structure. We'll call that a homopolymer. But we can, if we're just with two repeat units, with two monomers, we can start to play games. We can mix them up in a random or statistical fashion to make a statistical copolymer. Or we can carry out polymerization in a way which means that one will join on to the next and then go to the first and the next. So we have an alternating copolymer. Or using certain types of polymerization, what we call living polymerizations. This is things like anionic polymerization, or very specialized types of what's known as living radical polymerization. You can make a chain of one monomer, still have an active end, which will then polymerize on another monomer, so we can have what we call a block copolymer, two bits of the chain with completely different properties. And then they will associate in all sorts of interesting ways in solution or in the solid state. Or we can have a polymer where the backbone is one type and we graft something completely different onto the sides. And all of this changes the property. It gives a lot of scope for chemists to produce new materials for specific applications. So we've got a whole range of types of polymers. That is a question. If you've got a handout, you'll see that not everything is on the handout. Some of the information is there, and some isn't. And after the lecture, copies of the slides will appear on Blackboard. That's for the benefit of those of you who, for good reasons, dyslexia or something, cannot quickly take notes. But for most of you, I'd say it's always a good idea for you to take your own notes. Because what you write down to yourself, you're much more likely to remember than what you just hear or see. So it's always a good idea, even if you have a handout, to make your own notes that make sense to you. It all helps you to learn, it all helps you to remember. And anyway, we've got a couple of questions, so between us, can we answer these questions? So a common polymer is what we call polythene or polyethylene. Actually, there are quite a few different types of polyethylene. I've just mentioned two here, two broad divisions into what's known as low density and high density. So the sort of thing that's used to make flexible bottles and a lot of transparent wraps and such like is low density polyethylene. But the sort of thing that makes these sort of more opaque, slightly stiffer containers, that's high density polyethylene. Okay, so these are all polyethylene, same polymer, but actually the properties are different. So we have to ask ourselves, what's the difference? Okay, it's not the difference in chemical composition, chemically they're the same. But they behave differently because they have different structures. So the idea is, what's the difference between low density and high density in molecular terms? What is it different at the molecular level that gives rise? I mean, obviously there's a difference in density, as you might guess, but why? What's the difference at the molecular level? Any thoughts?
Different orientation of the monomer.
Different orientations of the monomer. There's something more fundamental here, but that can be important in other cases.
Number and location of the branches.
Rick's excellent answer. What's your name?
Robert Milne.
Say?
Robert.
Robert, okay? Good answer, Robert. The number and location of the branches. It's all about how much branching there is. Okay? Any ideas? Which will be the most branched between low density and high density? How does branching affect density? Which do you think of those two will have the most, in fact, long chain branches?
High density.
What do you think? Let's think about this. Here we've got a linear polymer. Now, density is all about how many molecules you can pack together in a bit of space, isn't it? Okay? So we've got a linear polymer, and think about how easy it is to pack that together. And polyethylene is semi-crystalline, so actually it crystallizes. And then imagine what happens if we start putting branches on the side. And these are quite long branches in the polyethylene we're talking about. How do you think that will affect the ease with which these molecules pack together?
Right. In linear branching, I mean linear polymer, actually the density is very low. Because the collagen
Because?
The branch at short distance is quite smaller volume. Therefore, the high branch having high density.
Actually, no. Can we try again? Anyone else want to have a suggestion? Because you've got to think about how easily the polymer chains can pack together. If it's a linear polymer, okay, and we stretch it out and has a regular structure, it can pack easily into a crystalline lattice. If we have little branches there, that stops crystalline packing. And so the polymer will be much more amorphous. There'll be less crystalline material. And amorphous involves more free volume, more space. So the more branched polymer is the lower density polymer. So low density polymer, it actually contains long chain branches. Now there is also, I haven't mentioned here, what's known as linear low density polymer, which again is branched and low density. But the branches are very small. They're actually produced by copolymerization. In this case, it arises. It's a high pressure polymerization process. Right, is doing that for us. And linear low density has a very different behaviour, but we've not mentioned that particularly here. But low density polyethylene is highly branched, long chain branches. The branches actually inhibit packing of the molecules. They actually mean that the polymer has a lower degree of crystallinity, more amorphous, non-crystalline material, and it's lower density. Whereas high-density polyethylene is more or less linear, only a few branches. Packing is more efficient, higher density, higher degree of crystallinity, different properties used for different things. Okay, something else you may have, sometimes they teach it at A level, another distinction you may have come across is the distinction between thermoplastics and thermosets. And I've already given a hint of that. What do we know about the difference between a thermoplastic polymer and a thermoset polymer? Someone up here must have some ideas. People?
He's quite crazy. It's like Carson with cocaine. Dangerous. No, he's like still on
Thermoplastic, when you heat it, it becomes plastic. You can flow, it can be reprocessed, it can be moulded. So all the sorts of things that we use to make, I don't know, Coke bottles. Somebody's got an illegal Coke bottle in the Coke bottles, which are normally polycarbonate, they're thermoplastics. So when you heat them up, they can flow, you can extrude them, you can mould them, you can do all sorts of things with them. Those thermosets are things which once you start out with something relatively low molar mass, you might then process it with something like compression moulding to make something like that light switch. But then, because it's a network structure, all the atoms are ultimately joined to all other atoms. When you heat it up, it might wobble a bit, but it won't flow. You can't reprocess it in the same way. And each has its advantages and disadvantages in different situations. So if you heat a thermoplastic polymer, it will soften, it can be moulded into a new shape, and it will have a linear or branch structure. But once you form the thermoset polymer, you can heat it as much as you like, it will degrade eventually, but you can't make it flow in the same way. That structure is fixed in the curing process. And it has a network structure, a three-dimensional interconnected network of some kind, linking all of the atoms. So we've got some examples just to see. So this is high-density polyethylene. So that's a thermoplastic. You'll notice that it's opaque. It's opaque because it is semi-crystalline. It has a high degree of crystallinity. We're going to talk more about crystalline polymers. This is polystyrene. That's another glassy polymer. You'll see this one is transparent. It's also more brittle. This is a glassy polymer. No, it doesn't crystallize at all. Again, we'll talk about why that is. And then this stuff, which is a phenolphthalein moulding powder. So in this form, it's relatively low molar mass. You put it into a mould, you heat it up, and it can be turned into a bowl or whatever you want it turned it into. But once it's cured, once it's been through that heating process, once you've formed it into a structure, that is then stuck in that state. It's a thermoset. Okay, so let's move on, just think a little bit about how we make polymers, synthetic polymers. So in all cases we have some sort of a reaction in which little molecules are going to be joined together to form a polymer. The little molecules we call monomers, the process we call polymerization. Hopefully you've all met this term before. And I've already indicated we can broadly break polymerizations into two groups, chain polymerizations and step polymerizations. And a chain polymerization is a chain reaction. Once it starts, it keeps going until something terminates it. And we need something to start it off. It might be a radical very often, it might be something else. And most chain polymerizations involve opening up a double bond or opening up a ring, and therefore it's an addition process. So most chain polymerizations can also be called addition polymerizations. So these are both terms which you will find in different books. Now a step or step growth polymerization is where you have a whole series of separate reactions occurring to build up a polymer. And a lot of step polymerizations, again not quite all, but a lot of them involve the elimination of something, often water, it may be something else. And so you'll also find the term condensation polymerization for many step growth polymerizations. So different books, you will find different words being used. You need to be aware of that. So let's just think about an example of a chain polymerization. Now, a lot of monomers for polymers that we use have a similar structure. They're what we call vinyl monomers, where we have basically CH2, a double bond, a carbon, and then one or sometimes two groups attached to that carbon. And so in the simplest case, we'll have just one group on the side, and depending on what that is, we get a different polymer. So if that's another hydrogen, if everything's hydrogen, then we have polyethylene. If we have an aromatic ring on the side, then we have polystyrene. Here's polystyrene. If we have a chlorine on there, we have polyvinyl chloride, and so on. So there's a whole range of polymers which start out from similar monomers, what we call vinyl monomers. And the simplest way of making one of these polymers is by a radical polymerization. We have something which degrades to form radicals either under heat or light. And of course, radicals are very reactive. We have a double bond, so we can open up that double bond to enable that to form a bond with that radical. But now we have a new radical which can now attack another monomer, and so on, and so on, and so on. So in a typical chain polymerization, just for a schematic illustration of what goes on, say we've got a load of monomers, these sort of blue blotches are meant to be monomers, and we have one molecule which is our initiator, which is something which under certain circumstances will decompose into radicals. Once you've got a radical, it's going to look around for something to react with. If it finds a monomer, it will attach itself to that monomer, creating a new radical center that's still reactive. It's going to look for another monomer, attach to that, create a new radical. This is a chain reaction. Once it starts, it will keep going, picking up monomers very, very rapidly until something will happen to kill off the radicals. For example, say if two radicals come together, we can get what's known as termination by combination. And there are other termination processes. Some of you will have met this already because we mentioned the kinetics of free radical polymerization in the second year kinetics course. Is that right? So this is familiar to you. And you will learn more about chain polymerizations from Professor Yates, I believe. The other class is a step polymerization. The classic example is a nylon we call nylon 6,6, which is made from two monomers. A monomer which has got two amines, a monomer which has got two acid groups. We know that an amine can react with an acid to form an amide, eliminating water. And so if we can push that reaction until all the monomers are used up, we'll end up with high molecular weight polymer. The guy who invented this was a guy named Wallace Carruthers, who worked at the American company DuPont. So he invented nylon in 1934. Unfortunately, Carruthers was a fairly depressive character and he later committed suicide. He didn't feel he'd achieved enough in life. But he was responsible not only for creating nylon, but also for laying the theoretical foundation for understanding step polymerizations, which was actually quite an enormous achievement. And a step polymerization of this sort, we call it an AA plus BB, because we've got two monomers, each with two of the same functional group. There are many other things you can imagine. This is a nice simple one. So if you imagine that the functional groups on the red molecules can react with the functional groups on the blue molecules, then if we just heat it up, add a catalyst, whatever is needed, any combination of molecules present can react. And initially we start to get a few dimers and maybe the odd trimer. We still have quite a lot of monomer present because it's pretty random what reacts with what. But over time you start to build up high molecular weight polymer. But what you will discover when you learn more about these is you have to push that reaction to completion, pretty much completion, before you get a really high molecular weight polymer. That's one of the difficulties of step polymerizations. And also you have to have perfect stoichiometry, or some trick. In the case of nylon 6,6, they got the stoichiometry by making a salt of the two monomers. because then you have an exact 1-to-1 ratio. If the stoichiometry is off a tiny bit, that you don't get high molecular weight polymer. And you'll learn more about that later in the course. So, just a reminder, the first part about physical properties of polymers, chain polymerization, step polymerizations, synthesis of polymers, that will be picked up by Professor Turner and Professor Yates later on. Now let's think a little bit in the last few minutes about what names we give to polymers. And if we go onto, if you go onto the blackboard, there is a file for you to download there, which has been kindly supplied by the International Union of Pure and Applied Chemistry, UPAC. You probably know UPAC are the people who think up of names and definitions for all sorts of things. Some people like the definitions, some don't. But they do have a set of rules for naming things. But I just want to draw attention to a few things about polymer nomenclature. You go away, look at that, that will give you more information. It's on Blackboard, you should already be able to. Has anyone who's checked Blackboard seen it? It should be there. Now, one thing you will find is that the same polymer may have more than one name. There are different strategies for naming polymers, and the reason I have different strategies is sometimes one strategy can get very complicated, so you try a different strategy. So you can have names which are based on source and names which are based on structure. So a source-based name means what we have is the name of a monomer, and in the simplest case we just say poly, the name of the monomer. And if it's a complex word for the monomer, we put it in parentheses. So if we have a monomer which we'll call vinyl chloride, our polymer is polyvinyl chloride. The other naming system is based on the structure that you get. Because of course a polymer may have more than one monomer go into it. Or in fact, polymers with the same structure may be formed from different monomers. And so sometimes it's better to look at the structure you've got, break it down, decide on a little bit of that structure, which we'll call a constitutional repeating unit. Then we say it's poly, that constitutional repeating unit. And actually you may be able to come up with different constitutional repeating units and therefore different names. And also a lot of polymers actually have traditional names that don't quite fit any of the rules, but they are so well known we still use them. And it's still acceptable to use them. So you will find in polymer nomenclature some words being used which actually have been abandoned in organic chemistry just because they're locked into the way industrialists talk about polymers. Let's have a look at a couple of examples. Let's start with the simplest polymer we can imagine. Simplest hydrocarbon polymer. Just a string of CH2s. So what names might we give that polymer? Now, we could call it polymethylene because that CH2 unit actually does have a liquid of methylene. Very rarely is it actually called that. Because of course, this is a polymer which is actually made from ethene. So you could call it polyethene, but actually the name for the CH2-CH2 unit is also officially ethylene, and it's more commonly called polyethylene, which is an old name in some senses. So the same polymer might be called polymethylene, polyethene, polyethylene, or often it's just abbreviated to polythene in general usage. So different names are all possible for the same polymer, but we've already seen that for this polymer we actually have different structural forms which have very different properties. So you need to be aware of all of these things. Let's have a look at this one. I've got 3 examples here. They're all the same polymers, the same repeat unit. Here's one. It's a liquid. Here's one. It's a sort of a waxy solid. And here we've got a powder. It's all the same polymer. What's the difference? Actually, the difference here is how big the molecules are, which is why later in the course we're going to ask questions about how we work out how big those molecules are. But the repeat unit is OCH2CH2. So the constitutional repeat unit here is O-oxyethylene. So we can call it polyoxyethylene. But we can make it from two completely different monomers. And generally, low molecular weight samples are made from ethylene glycol by a condensation reaction, and higher molecular weight samples are made from ethylene oxide by a ring opening reaction. You end up with the same repeat unit. The end groups will be different depending on the polymerization, but the same repeat unit in the polymer. So you will find this polymer referred to as polyoxyethylene, as polyethylene oxide, as polyethylene glycol. They're all the same chemical structure in the backbone. But usually polyethylene glycols will be fairly low molar mass because it's hard to push this to high molar mass, and usually polyethylene oxides will be high molar mass. They are all polyoxyethylene. Okay, so just to finish off, here's another monomer. This monomer has the official name 2-methyl-butyl-1,3-diene, but we more commonly treat it as isoprene in polymer science. Okay? What polymers might we make from this? Now, we've got 4 carbons here and 2 double bonds. So we can label 5 carbons, but we'll label the ones in the main chain 1, 2, 3, 4. And we can do a number of things. We can add from 1 to 4 in different ways, or we can add 1, 2, or we can add 3, 4. To add 1, 4, we've now got a double bond in the middle, and so we now have different, what are sometimes called geometric isomers, or cis-trans isomers. And if we have the cis form, where the 2 bit chains are going off in the same side, we have cis-1,4 polyisoprene, that's what we call natural rubber. The trans form is also found in nature, but it has very different properties. That's gutta percha. But synthetically, we can also make a polymer by adding 1,2, so we have 1,2 polyisoprene, or 3,4, so we have 3,4 polyisoprene. So depending on how we do the polymerization, or how it's made in nature in a tree, in the case of natural rubber in Hevea brasiliensis, we come up with polymers with different structures, different properties, but all based essentially on the same monomer. And that's it for today. Tomorrow we'll talk more about natural polymers.